I welcome you to our short presentation, and this is just basically aimed at being a tutorial so that we can discuss a few things that we talked about in class. So on this particular case, I was thinking we talk about electronic configuration, right? We talk about the electronic configurations. But first, before we go to that, I was thinking maybe we try to consolidate on parts of the atomic structure that we're looking at, where we talked about the quantum numbers. So I was thinking maybe we start with that. We consolidate on, I know that most of you have been to my office to discuss about the quantum numbers, so I thought maybe we start looking at the quantum numbers. And in this particular sense, I'll be a bit practical in my approach so that you can know how you... So with the quantum numbers, there are actually four. The first one is a principal. The second one is an angular. And the third one is a magnetic. And the fourth one is a spin quantum number. So the principal quantum number just tells you about the energy level, and it's abbreviated by N. Then the angular tells you the shape of a subshell and it's abbreviated by the letter L. Then magnetic tell you how many of each shape and it's abbreviated by ML. Then you have a spin. A spin just tells you about rotation, meaning one is rotating clockwise indicated as plus half and the other one anti-clockwise indicated as minus half. So you have four quantum numbers. Now, how are these quantum numbers related to one another? So this is the principal quantum number, meaning the overall. Then this is the angular quantum number, meaning it tells you about the shapes. Then this is the magnetic, it tells you how many of the angular orbitals from each. Then you have the spin. So let's start with, I'll have a different approach to this. I'll be using examples. Let's start with carbon as our example, right? Carbon has 6 electrons. So now, what are the sets of quantum numbers for carbon? Then if you are to draw the electronic configuration for carbon, you will discover that you have 1s2, 2s2, and 2b2. So in short, what you have for carbon, it has 6 electrons, which the 2 goes into the 2s, so the 1s, 2s, and 2p. So now, what we have from here is that, what are the quantum numbers for these each electrons? So we can list them. So electrons, there are 6. So there's 1, 2, 3, 4, 5, 6. We want to know. Then the principal quantum number, which is N. We know that 2 electrons are in N is equals to 1. So 2 electrons are in N is equals to 1. Then 4 electrons are in N is equals to 2. So you know this prefix here is N. So this prefix here gives you the principal quantum number. So meaning 2 of these are in 1. Then 2 of these are in 2. So you have 2, 2, 2, 2. So there are 6 electrons. 2 electrons are in N is equals to 1. and 4 electrons are in N is equals to 2. Okay. Now we determine let's say 6, 12, 1s2, 2s2, 2p2. Now we determine the angular momentum. The angular momentum is given by L. And you know from the lecture notes, we know that L is equals to N minus 1, and L is represented by 0 to N minus 1. So this is the same way it is on the number line. So if you have 0 to N minus 1, it means if it is, let's say for example, if in this case, let's start with the first one, N is equals to 1. So when N is equals to 1, L will be equals to 1 minus 1 equals to 0. So when you use this principle, it will be 0 to 0. So it's just basically 0. So for these 2 electrons, they are in the 0, 0. Right? Then you go to these 4 electrons. With the 4 electrons, what you get, you have N is equals to 2. So L will be equals to 2 minus 1, which is equals to 1. Then if we use this rule, it will be 0 to 1. So in short, you have 0 and 1. Then, from what we looked at, we know that 0, 1, 2, 3. So this is S, P, D, F. So 2 electrons are in the S here, so you have 0 and 0. And 2 electrons are in the 1, so we have 1 and 1. So what it means that this electron is in the S, 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 P, and P. Then we go to the magnetic quantum number. So the magnetic quantum number basically will be ML is equals to minus L2 plus L. So it's more or less like a number line. So for the first one, then we go to ML. So for the first one, what we get is that L is 0, 0. So in short here you have 0, 0, 0, and 0. Then for this is when L is equals to 0. When L is equals to 1, what you get, ML will be equals to minus 1, 0, 1. So there are 3 orbitals. So you can choose any of these 2. So what you get is that 1 will be in the 1, and the other one will be in the 0. Or if you want to get a plus 1, 0, or minus 1, 0. Then for the spin, it's very easy. 1 will be plus half if they're in the same energy level, and 1 will be minus half. Same applies here, plus half, minus half. Here now, since these are 2, the p orbitals are 3, there will be 1, 2, 3. So according to Han's law, they should be singly filled first. So you have 1, 2. So meaning this will have a positive, and this will have a positive. That's how we write the principle. Also, that's how we write the quantum numbers for carbon. So meaning what we're looking at is we are looking at the quantum numbers of each electrons in carbon. So if you're given this, then they ask you, write the principal number of the valence electrons. The valence electrons are the one in the outermost energy, the principal quantum number. So this is the outermost principal quantum number. So the valence electrons are basically going to be this. Then what it means, it's all these electrons starting from here, going downwards here. Then according to Pauline's exclusion principle, it says no two electrons will have the same set of quantum numbers. For example, you can have these two. These two are in the 1s2. So you see, the principal quantum number is 1, 1, it's the same. L is 0, 0, the same. ML is 0, 0, the same. But the difference now is a plus, half, minus, half. So no two electrons will have the same quantum numbers, because in most cases, most of them will be aligned in opposite spins. Okay, we move to another example. Let's go to phosphorus 15. When we write the electronic configuration for phosphorus to be equals to 1s2, 2s2, 2p6, 3s2, 3p3. So note that if you're writing this, let me express this. This is a 1s like this. This is the number of electrons. This is the shape of an orbital, and this is the principal quantum number, which is n. Then we note that each orbital can accommodate 2 electrons. So each orbital can accommodate 2 electrons. Now we can use the magnetic quantum number to determine how many orbitals are there for each. Let's say, for example, if you have S, right? ML is equal to 2L plus 1. For S, L will be equal to 0. So what you have is L is equal to 0, 1, 2, 3, 4. So this is S, P, D, F, and the list goes on and on. So now what you get is that using the magnetic quantum number, we can determine how many of each orbitals are there. So let's say, for example, for S, SL is equal to 0. So when you substitute L for 0 in here, what you have 2, 0 plus 1, meaning 1. So in short, for the S orbital, there is only one type of an S orbital. So what you get is that in every principal quantum number, there will be an S. So there's only one type of an S orbital. Then let's go to when S is equals to, so for P, L is equals to 1. So this is ML, 2, 1 plus 1 equals to 3. So the P orbitals are actually 3. So you get the PX, PY, and the PZ. These are the axes in which each one of them is oriented. So this is circle like this, and these are more or less like dumbbells based on the orientation in the shape. So if this is in the x-axis, it will be like this. In the y-axis, it will be like this. And in the z-axis, it will be like this. They are shaped like dumbbells. And one thing you should note is that all of these three exist at the same time. Now, for simplicity's sake, we draw them each one by itself. But in reality, this and this and this exist at the same time. So you have the 3-dimension. You have something that looks like this. So this is a y, z, and x. So all of these will exist like this. Now, for simplicity's sake, you can draw them in this particular case. Then you go to the d orbitals. dl is equals to 2. So ml, 2 plus 1 is equals to 5. So these are 5. Then the f are 7. Then note that each subatomic orbital is able to accommodate a maximum number of 2 electrons. So what you get, if this is 1, this can get 2 electrons. If these are 3, they can get 6 electrons, because 2 each. So 2 times 3, 6. So if these are 5, they get 10 electrons, and this gets 14 electrons. So this assists us on how to distribute the electrons in the electron configuration like this. For example, this can get up to 6. Now, what we want to do is that in this example, we want to look on the quantum numbers in the valence shells. So the valence shell is the one in the outermost. Outermost is the one that is furthest from the nucleus. So this is the outermost subshell. So now let's write the principal quantum numbers of this. So now what you get is that there are 5 electrons. So you have 1, 2, 3, 4, 5. That is in electrons. Then n, for all of them, n will be equals to 3, 3, 3, 3, 3. So this is n is equals to 3. Then ml. For L, it is simple. You can have like L. So now what you get is that from this, here's a basic rule that you have to employ. Using Hand's rule, these are 3. Then the P can accommodate 6. So the 3 will first be singly filled before they are paired. So in short, each one of them will go into a different orbital. Then from the orbitals, what we have is that ml is equal to minus L to L. So for 3, then S, for SL is equal to 0. So this will be 0, 0. So what you get, you have 0 here and you have 0 there. Then these 3 electrons, starting from here, so this is 4 and 5. So starting from here, each one of these is in its single orbital. So now what you get is that PL is equal to 1. So when we use this concept, you have minus 1, 0, plus 1. So meaning each of these 3 electrons, one is in here, one is in here, one is in here, because they are singly filled. So when it comes to this, what you have minus 1, 0, plus 1. Now note the 0 here means a P, it's not a Z. It is coming from here, not the other one. Then the ML. Okay, I think for L, this would be 1, 1, 1. So it is the ML where you have 0, 0, minus 1, 0, plus 1. Then with a spin, that is MS, this will be plus half. Since there are 2 of them in the orbital, the other one will get a minus half like this. When you come to this, this will be plus half, plus half, plus half. So if we were to draw this using the boxes, we know that this is phosphorus, it's 15, 2s, let's say 1s2, 2s2, 2p6, 3s2, 3p3. So if we were to use the boxes for the final electrons, what we get is that the 3s2 will have two electrons with the opposite spin. So this is what you have, a positive and a negative. Then for the 3p, there will be three of them. 1, 2, 3. So this is 1, 2, 3. So this is +1, 0, and -1. So this will get +1, 0, and -1. So one is the px, py, and the pz. Each one will get a single field. Now, since all of these are pointing in the same direction, so this would be equal to +half, 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 like that. So here is the thing. The other thing that I was trying to see the comments that you have there is that the other thing that you have is that your connectivity. So if you can't see very clearly, try to check that you have a proper connection of internet. Then you need to be able to know. So your connectivity also has to be very good for you to be able to see. So just try to see if you have a proper connection of internet, then it will improve on the picture quality. Then one says that I'm far from the board. I think this is the best I can get, because if I move the camera a bit further, it's going to cut some of the sections of the board. So I think one of you was asking, why are we just using the last electrons? Because we're just looking at the valence electrons. So the valence electrons are the ones in the outermost shell. So basically, what we were looking at is that we were trying to write the quantum numbers for each electrons. Now, if you look at phosphorus is P15. You can actually write the quantum numbers for each and every one of these, which meaning 15 electrons, and it will be a bit cumbersome. So, just a quick revision. Let me see if we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Let's do the first 10. So phosphorus would be 15. So you have 1s2, 2s2, 2p, 6, 2. So 3s2, 3, 5. So we've already done this. Let's also do this and see what we have. So these are the electrons in phosphorus. So we want to establish the quantum numbers. So for N, we know that these two are in N is equals to 1. So here it's 1, 1. Then these two, its N is equals to 2. So 2, 2. This is also 2. So you have 2, 2, 2, 2, 2, 2. So meaning 8 electrons, 1, 2, 3, 4, 5, 6, 7, 8 are in this. N is equals to 2. Then 2 electrons are in N is equals to 1. Then we can go to L. It's very easy. So for L, what we have, L is equals to N minus 1. Then this is 0 to N minus 1. So for N is equals to 1, L is equals to 0. So meaning this will be 0, 0. Then when N is equals to 2, L will be N minus 1, 2 minus 1, which is equals to 1. So when we use this, we know it's 0 to N minus 1. So you have 0, 1. We use the same way we use on the number line, right? Then we know the 0 is an S, then the 1 is the P. So meaning electron number 3 is in a 0, 0, which is an S, you see? S here. Then electrons starting from number 5, they are in 1. So what you're trying to say is that this is in the S, this is in the S, and these are in the P, 6 of them. So you see, there's 6 here. So there's 1, 2, 3, 4, 5, 6. Then there's 2 here. So you have 1, 2. There's 2 here. So you have 1, 2. So that's how you represent the electron. Then we go to the magnetic quantum number, which is the ML. Now, with the magnetic quantum number, what you get is that ML is equals to minus L2 plus L. So here we know it's 0, so it will be 0 to 0, which is equivalent to 0. So meaning this and this is 0. So we also get to this will be 0 and this will also be 0. Then we get to the P, right? 1, which is a P. So for P, when L is equals to 1, this is equals to minus 1, 2, plus 1. So now this is the way it is on the number line. So it passes through 0. So this will be minus 1, 0, plus 1. So in short, what you get is that 2 electrons will be the plus minus 1, 2 electrons will be the 0, and 2 electrons will be the plus 1. Remember the rule says an orbital can only accommodate the maximum number of 2 electrons. So what we have is that this will be minus 1, 0, 0, plus 1, plus 1. Then we go to the spin quantum number, which is the easiest of all of them. Spin quantum number, there are only 2 possibilities. There is one is a clockwise, indicated as a plus half, and the other one is a counterclockwise or an anti-clockwise, which is indicated as minus half. And that's what you do. So this will be plus half, minus half, 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 like this. So this is how you present the quantum number. So it's very easy to write the quantum numbers of all the electrons in in the structure. So now, let me write the same thing using boxes, right? So we know if we use two boxes, let's say this is an increase in energy, increase in energy. So we start with a 1s, 2s, 2p, 3s, and 3p. So the s will have a single box, S single box, because S there's only one type. The P's will be 3. 1, 2, 3. S again 1. Same applies 1, 2, 3. So what we get now is that in the S there are 2 in the one S there are 2 electrons and opposite spins. So there's this pointing up, pointing down. Up, down. Here there are 6. So this is 2, 2, 6, 2, 3. So here is first singly filled 1, 2, 3. Then you start pairing them. Pair, pair, pair. 6. Same applies here. First singly filled, then you pair. If there's excess of electrons, you go to the next energy level. Now here there are only 3, and there are 3 orbitals. So there will be half, 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 like that. That's how you represent the electronic configuration of the structure. And I think with this and with your studying, okay. Okay, so with this also we will let's look at electronic configurations, like and how you configure electrons in. So the question is, in the electronic configuration, how would you know that the 1s comes first than the 2s, then the 2s comes first than the. So the principle that we use basically is what you might call as the off principle. So this helps us to align the orbitals. So it only looks at the subshells, meaning you have the main shell, which is the principal quantum number. Then inside the principal quantum number are what you normally call as the subatomic orbitals, meaning the subshells. So what you get is that you first write 1s, 2s, 2p, 3s, 3p, 3d, 4s, 4p, 4d, 4f, 5s, 5p, 5d, 5F, 6S, 6P, 6D, and 6F. Okay, the orbitals goes, but we just end here for simplicity's sake. Then according to Aufbau, you draw an arrow. Now an arrow starts from the top coming down and it's diagonal. So you have the first one goes like this, the second one goes like that, the third one goes like this, the fourth one goes like that, then it goes like this, then it goes like that, then it goes like this, then it goes like that. So now, in terms, you start from here and end here. So meaning, this is your start point. You start from here, you end from here. Then you go, you start from here, you end here. You start from here, you end here. You start from here, you end here. You start from there, you end here. You start from there, you end here. You start from there, you end there. So now, how do the orbitals go? So how will be the subshells going to be aligned? You know, so we have 1, 2, 3, 4, 5, 6, 7, 8. So in the first one, there is only the 1S. Second one, we start from here going down there. There is a 2S. In the third one, we also start from the top. So the top is a 2P, then 3S. We come to the fourth one. It's the 3P and the 4S. We start from here. 3D, 4P, and the 5S. So the list goes on and on. So now this gives you the electronic configuration. Note that from here is that the 4S come earlier than the 3D. The 4S will come earlier than the 3D. Then note that each one of these shall only accommodate a maximum number of 2 electrons. So it's only 2 electrons. Here 2. Here there's 2 times 3. 6. Here 2. Here 2 times 3, 6. Here 2. Here 2 times 5, 10. Here 2 times 3, 6. So that's how you distribute the electrons. Now when you're writing the electrons, you just write the total number of electrons here. So the total number and the superscript. So we can look at examples or different examples. All right. So we have, let's start with the simplest one, carbon. How would you write the electronic configuration for carbon? It's very easy. The first thing that you do is, you know, there are 6 electrons, so you need to occupy the 6 in the orbital. So now what you get first is the 1s2. Now, one thing you should note is that one orbital has to be filled first before you go to the next orbital. So since there are 6 electrons, so when this gets 2, so you're remaining with 4. So the 4, amongst the 4, the 2 will go into the 2s2. How many are remaining? Only 2. So you get 2p2. So when you add this plus this plus this is 2 plus 2 plus 2, it gives you 6 electrons. So these are the 6 electrons that you get. We got to which are okay, phosphorus, the one that we're looking at, 15. So you distribute, the first will go into the 2s2, so 13 are remaining. So the other one, 11 are remaining. So this is 10, meaning they're remaining 5. So 5, 2 will go into the 2s2, and 3 will go into the, like this. So when you write the electronic configuration for phosphorus, it will look like this. Very easy, right? So you can draw electronic configurations of different atoms that you like. Then, using the same, we can also write for neon, right? Neon has 10. Neon is a noble gas. It's in group 8. So it's called a noble gas because it's non-reactive. So what you get for neon, you have 1s2, 2s2, and 2p6. So this is the electronic configuration of a noble gas, which is neon. So we can use this for a shorthand writing. So to represent the electronic configurations of neon, you can actually write it like open square bracket, neon, and a closed square bracket. So this has the electronic configuration of 1s2, 2s2, and 2p6 like this. So in short, if we go to phosphorus, you can, this is close to neon. So instead of writing like this, we can write something like that. So from here, what we get is that with phosphorus, this is electronic configuration of neon like this. Meaning this now becomes like 3s2, 3p3 like this. So this is for phosphorus, like the shorthand electronic configuration for phosphorus. And there are some rules that we need to understand is that when it comes to filling up the electrons, the fully filled is the most stable. The single filled is a bit stable than the partially filled orbital. So fully filled more stable, followed by half filled, then the least is the partially filled. So you can look at different examples on the periodic table and see how you can write the electronic configuration using these principles that we have.